Hello, folks. Welcome to my talk, Chrome OS Virtual Machines. It's virtual machines all the way down. I'm Zach Reisner, and I've been a Chrome OS developer for 6 years, and I've been working on Chrome OS VMs for about 4 years now. I'm here today to talk about the many wonderful applications of virtual machines on Chrome OS, which have experienced somewhat of a Cambrian explosion in recent years. This talk is to help you map out the VM landscape. So just to start with a quick overview of what we'll be covering, I want to talk about the history of Chrome OS virtual machines and the various kinds that there are. We'll be talking about 4 different kinds today. I'll also be talking about the so-called Crostini daemon constellation, which is, you'll discover what that means shortly, as well as the security of the virtual machines, which is definitely a theme of all of the virtual machines on Chrome OS. We have a big focus on security. So just to talk about the history, let's set the stage. It's all the way back in 2016. We have these ludicrous speed Chromebooks for our power users to use, but what exactly are they supposed to use them for? Also, meanwhile, we have these flexible Arc++ framework containers that can run Android apps, just like their smartphone can. But they can't really do anything else with them besides run smartphone-style apps. There just has to be a cool use for all this software and hardware power. So the other thing we're thinking about, concurrently with this is that for Apple users, or for Apple developers, I should say, when they want to develop for mobile applications, they can use, and in fact have to use, their Apple computer to do so. Even though Google has its mobile operating system, there's no Google hardware to develop for it. We have Android Studio, but you have to run it on a desktop operating system like OS X or Windows. So this kind of got us thinking about what we could do, for our developers to make it so they could use Google hardware to develop for Google mobile operating systems like Android. The result of this was Crostini, which I hope some of you have heard of today. That's also known as Linux, currently in beta. Linux for Chromebooks, currently in beta. So what this provides to our users is a container which is fully under their control, and they can run all kinds of applications such as Android Studio, and it's been a big success. Just to give a taste of previous versions of this talk, we used to go deep into each of these little topics here. It's gotten even more complicated, and I don't really want to go over them because I've done that in previous talks, but I think this talk deserves a little bit of information. The overview is that we provide an LXD container, which is sort of like a Docker container, if you've heard of those, which is fully read-writable by our users. They can choose any container they like, but we provide one that just works, which is based off of stable Debian. Crostini uses LXD inside a read-only Chrome OS-derived image called Termina. Termina provides both a Chrome OS rootfs and a Chrome OS kernel. This is all executed inside a hypervisor program called CrossVM, itself an ordinary binary running in the Chrome OS user space. CrossVM makes use of KVM provided by the host's Linux kernel. So that's to recap, that adds up to 2 kernels, host and guest Chrome OS flavor Linux, and 3 root file systems, 2 Chrome OS and 1 Debian. But we get a lot out of it. As you can see here, I have a screenshot of Firefox, Sublime Text, a terminal running HTOP, and a 3D rendering program, that's GLX Gears there, running all on my Chromebook. We even get application shortcuts on the bottom. You can see Firefox and Sublime, as well as the terminal icon on the bottom there. So that was a little bit about Crostini, which was the first virtual machine application we did for Chrome OS, but there's a few others to talk about. In order to help map things out for you, I have somewhat of a Venn diagram. Just to clarify, everything here uses CrossVM in some capacity, which is why I have the little key in the corner that says, CrossVM, and the white color corresponds to that. So when you hear terms like Crostini or ArcVM, I want you to have an idea of what that means and the subprojects that constitute it. There is no Crostini binary, but there are several daemons, both host and guest side, that support its execution. You can see that, for example, Crostini uses Termina and Debian and LXD as part of its ability to serve Crostini, but it's not used by other VM applications like Parallels, Manatee, or ArcVM. Those have their own components that make it up. This certainly isn't exhaustive as far as virtual machines, and I expect there to be more of them in the future, but this is what we'll be talking about today. So probably the most close to Crostini that isn't Crostini virtual machine that we have is ArcVM. It's the long-awaited next generation of Android app support on Chrome OS. Formerly, Arc++ was written as a container against the Chrome OS kernel, necessitating that the Chrome OS kernel itself had substantial Android-specific features like binder. Simply between merging kernels and passing Android CTS, this is a maintenance nightmare that has been a bit of an albatross around the progression of Android and Chrome OS's kernel developers. Additionally, a simple kernel exploit is all that was needed for an app with native code to compromise Chrome OS's system. This is the reason that ArcVM is being pursued today. It is the potential to speed up kernel uprevs, smooth over incompatibilities, and improve on our security position. Technically, it means that Android now has to use the para-virtualized devices provided by CrossVM and integrate with the daemon constellation, which we'll be getting into shortly. Because Android demands hardware support that wasn't formerly found in CrossVM, such as accelerated video decoding or rendering, enhancing CrossVM has taken a substantial amount of work. That's work to support ArcVM. But because it will be running inside of a VM, instead of running directly against the guest kernel, we'll have that increased isolation. Another VM application in Chrome OS is Parallels. Parallels is actually a company that had provided Windows and still does provide Windows VMs to OS X, and we found that it would be of value to Chrome OS users as well. It still uses CrossVM under the covers, but in a very different way from the other virtual machines on Chrome OS. We still sandbox Parallels, but it runs its own closed source binary that talks through KVM indirectly through CrossVM. Unlike the other VM applications, CrossVM doesn't provide any of the para-virtualized hardware. That's all provided by Parallels, as well as the launcher and UI window that you see in that screenshot there. But because we provide that isolation, we can be fairly certain that there won't be as many security problems as there might otherwise be in an unsandboxed scenario. And finally, the fourth kind of VM that we're talking about today is called Manatee. So Manatee is itself named after its goal of realizing a trusted execution environment, or TEE, for Chrome OS, which is standard and vendor neutral. The idea is that Chrome OS itself will run inside of a thin hypervisor host, and most of the memory and hardware will be passed through into the guests. That is substantially the same as bare metal Chrome OS of today. That is, we will use the same kernel hardware drivers that run against the bare hardware will work against the passed-through hardware. This will allow us to have an isolated sibling guest OS that can do secure, trusted computing operations while still taking advantage of the powerful processor of the main processor of the Chromebook and the pertinent peripherals. I'm demonstrating this here with this diagram. You can see we've got the bare metal, which today Chrome OS just runs on the bare metal, would now have the Manatee layer that isolates it, as well as the sort of sibling operating system, the trusted execution environment. In this environment, we would also move Crostini out from under Chrome OS, where it is today, as another sibling. This is just to get around the fact that nested virtual machines incur a penalty, and we'd want to basically reparent the virtual machines to avoid that nested penalty. So this is all still implemented using CrossVM again, but the addition of Linux's VFIO module allows us to use the IMMU. This tag is most famously used by folks to run Windows guests on their Linux desktop with a powerful discrete graphics card passed in to enable Windows-only gaming on their Linux desktop. Now, the IOMMU, bit of a mouthful, is important for Chrome OS so that hardware can still run at full speed, including hardware that requires direct memory access, such as your GPU accessing, textures or the frame buffer, without risking the sensitive memory of the trusted computing environment. So in that scenario, the GPU can access its memory that it needs for textures directly on Chrome OS's system memory, and it can't be fooled because of the IOMU into accessing secure memory that the trusted execution environment might have. It'll have secrets on there like biometrics or encryption keys, which shouldn't be leaked. The upshot is that Chromebooks can ship with fewer expensive chips that add to the cost of Chromebooks while enabling features such as biometric unlocking. Today, Chromebooks without this Manatee environment, they have to have a separate secure enclave-like chip in order to do these things, and they have to have a lot of power just to do biometric processing. And we'd like to reduce the need for those things while simplifying the architecture of it. So the VMs all have something running on the host side and on the guest side. For demonstration purposes, I'm going to be talking about Crostini, but this isn't true for all the other kinds like the Manatees and the ArcVMs. They all have their own sort of host side, guest side daemon pairs. But yeah, just using Crostini as a reference point here. And this is getting into that constellation of daemons I was talking about before. It isn't just CrossVM that's running the VMs. It's maybe we're doing the lowest level pieces of physically executing, but there's stuff on the outside supporting it. So, okay, talking about Concierge. What is that? It's responsible for the life cycle of CrossVM. So Concierge is a daemon that'll be running under Chrome OS, and it's listening on dbus for instructions to actually start a VM. So, for example, when I click the Firefox button on my toolbar to actually launch a VM, Chrome will communicate over dbus to Concierge to actually execute CrossVM if there's not already a VM running for it. And so the pair part that I've been referring to is that Concierge will be talking to maitre d, which is its counterpart inside of the Crostini VM, which will confirm to Concierge that it actually is running. And it will help bootstrap things such as the networking and starting up the container runtime, LXD, in the case of Crostini. For other VMMs, there's different programs for this, but it's similar, right? You got something that is starting CrossVM and something on the inside which sort of executes the will. CrossVM is written to be agnostic. It doesn't necessarily know what kind of guest it's running. It just does the sort of bare metal execution that all VMMs need. Another piece, and again, specific to Crostini, but worth talking about, is the Garcon/Cicerone pair. So this is started in the sort of container phase of Crostini when we actually, running Debian. So we use LXD to start the Debian container, and this is handled using Tremplin and Cicerone, which you can see in the diagram. Tremplin is a simple proxy for the LXD daemon that Cicerone can communicate with. Cicerone and Concierge were at one point the same daemon, but were separated for security purposes. Cicerone's other job is communication with Garcon, which is analogous. Cicerone's other job is communicating with Garcon, which is sort of like maitre d from the previous slide. It's like a init process, except it's running inside the container instead of the bare the main process of the guest kernel. Garcon is responsible for a lot of the integration that you see as a user on Chrome OS with Crostini containers. So it'll actually launch. It'll actually finally launch Firefox when it's commanded to by Chrome through dbus through Cicerone. And it'll also do other things back to Chrome. So for example, you open a web page using a link inside of, say, your terminal emulator or something that you're running inside of Crostini, will handle that, and it'll actually be handled by the host Chrome if you've configured it such that way. That's sort of the default. So we've talked a little bit about the daemon constellation. I want to talk a little bit about the low-level details of CrossVM and how it runs and how we achieve that security. Here's a very high-level view of how that works. We start with something that is able to execute machine instructions, hopefully quite fast. For CrossVM and Chrome OS, this is all using Linux's KVM module, which interfaces with hardware virtualization support on Intel, AMD, and ARC64. That's 64-bit ARM devices. Then we perform setup on this VM, such as filling in the guest physical address space with memory, pre-initialized with the operating system image, and setting up the registers to start executing the kernel's main function. We're sort of like the bootloader, like Grub, for our guests. We don't actually run those today. We just kind of do things that they would do in CrossVM directly. This is one of the reasons we're able to boot up so fast. Finally, we create vCPUs in ordinary host user space threads and let them execute. Anytime the guest wishes to access virtual hardware that CrossVM implements, the KVM functions return with detailed information about the machine and why it returned. And we use that to execute the correct virtualized hardware routines. Every VM works like this, including QEMU, which is what we initially explored for using with Crostini, and by extension, the other VMs that are in use in Chrome OS. Unfortunately, QEMU has a bad history of exploits related to those virtual hardware routines I alluded to earlier. Because the guest has basically direct access to those virtual pieces, it can use those to sort of gain a foothold in exploiting the host operating system. Knowing this, our plan was to use a smaller, less full-featured virtual machine called KVM tool, hoping that less code meant less bugs. Even this proved futile, though. It was midway through our development cycle, our security team advised us that KVM tool would need a full audit or to be rewritten. Knowing that a simple C or C++ rewrite would likely end with a similar memory safety problems, we decided to experiment with Rust. For those unfamiliar, Rust is a memory-safe language designed to fill similar niches to C or C++. Having no active runtime and safe access to memory was a perfect fit. So perfect, in fact, that we're even starting to use Rust in more and more places across Chrome OS unrelated to VMs. We haven't stopped there, however, as far as safety is concerned. We take a belt and suspenders approach to security, and merely raising the bar on memory safety isn't enough. CrossVM puts each device into its own sandbox process, as can be seen in the diagram. Those are the yellow boxes that you see. How does this work in practice? Take the block device. That's the Verdeo BLK one in the middle, as an example. The guest communicates with that and many other devices using the Verdeo protocol. This protocol is mostly done using ring buffers and guest memory. Because guest memory is actually just ordinary shared memory with CrossVM, we can share it with each of the sub-processes as well. Therefore, the devices themselves can communicate directly with the guest through its guest memory, often without involving the main CrossVM process at all. Because the task for each device is so well defined, CrossVM is able to sandbox them using minijail, which is the Chrome OS specific sandboxing library, which we use all over Chrome OS. For block device, this means the set of syscalls it's able to use is very limited using seccomp. Its mount namespace is nearly empty, so ironically, it actually isn't able to open new files, even though its main purpose is to give access to a main block device to the guest. And it has no access to things that are unrelated to its function, such as networking. As you can see on the diagram, the Verdeo net device would have access to the TapFD. That's sort of like a virtual Ethernet plug, but no one else would. None of the other processes would. For the sake of argument, Say an untrusted guest program were able to exploit the block device process and gatefold execution inside of that Verdeo block environment. Unlikely as that may be, the attacker would have little to gain from this. Because everything is so tightly sandboxed, they would have access to the disk file, which it already was able to access as a guest, and basically nothing else. The host kernel is protected because the syscalls are limited. The file system is protected because it's given basically a blank looking file system. And the other devices aren't even part of the same process. They're using separate memory. So, things are very well protected by this. So in summary, we have I discussed the history of Chrome OS virtual machines, how they were inspired by us wanting to give our developers a reason to use these ultra powerful Chromebooks. And on top of that, we want to be able to say that you could develop Google or develop for Android on a Google device. And we've sort of just been expanding the use cases ever since then. We explored the kinds of virtual machines of Chrome OS. So starting from the original Crostini use case, which was just Linux on Chromebooks, to ArcVM, which allows us to have more secure, more easily developed Android environments for Chrome OS. We talked about parallels, which we are giving to, or which we're providing to our enterprise users who really need to use Windows applications, but so they can still use Chrome OS to do it. Talked about Manatee, which we're going to be using, which is yet to be deployed, but we will be using to enable these sort of trusted execution environments at reduced cost and more simply than with using an extra chip. We talked about the Crostini daemon constellation a little bit, which was an overview of how it isn't just CrossVM or any single program that makes Crostini or any of the VMs on Chrome OS, but is in fact a whole collection of daemons which support its functioning. And we talked a bit about the security and how it's provided, by many different layers. We talked about how Rust and its memory safety prevents us from having exploits to begin with. How if there is an exploit, however unlikely, the multiple processes protect the devices from one another. And we talked about how the sandboxing within each process protects the host operating system from those devices. So I've given other talks about that go into way more detail about Crostini. Here's a README document that we update about everything, as well as a few prior talks that I've given. Those things go over a lot more of the daemons, precisely how they communicate with each other, a little bit about, or actually quite a bit about, how we achieve specific integrations like windowing. Not much has changed since then. I would say the biggest difference is that it's harder and harder to hold it all in one person's head. I guess that's a consequence of the flexibility of the system, is that more and more people can contribute to it, and therefore you don't have to keep it all in your head. So I've been instructed to say that I'll be in the hallway discussion track if people have any questions. I don't know if anyone's been asking questions. I guess not any questions during the thing, but I'll be there to discuss anything if anyone wants to talk about it. Thank you so much for coming to my talk. I hope it was informative.